29, and those are the notes. So let's document what we did here. Okay, I uploaded the correction for homework 2, 3A, 3B, and exam 2. I uploaded to your personal folder the correction of homework 2, 3A, 3B, and 2, and exam 2. We finished chapter 6 last time. 3. Looking here at the schedule, right? Homework for chapters 4 and 5 are due today, 11:59. Homework for chapters 4 and 5 are due today at 11:59. Exam 3 will be for chapters, will be for chapters 4 and 5. That's going to be the last partial exam. This is the last partial exam. This is the last partial exam. And I dropped the lowest grade of the partial exam. In the calculation of your final grade. Okay? The final exam will cover the whole material and will be next week. All chapter will cover all chapters, and will be next week, and it will be held next week. That's what we have here. Anything else, right? So just summarizing from last time, there are 4 laws of thermodynamics.
Professor, we can't see your screen.
Oh, thank you. Thank you. Yeah. I thought I was showing the screen here. Yeah, now you can see, right? Here you go.
Yes.
Okay, I upload to your personal folder the correction of exam 2, 3A, 3B, and exam homework 2, 3A, 3B, and exam 2, right? We finished chapter 6. Homework for chapters 4 and 5 are due today at 11:59 p.m. Exam 3 will be for chapters 4 and 5. Exam 3 will be held next time, right? And we'll cover chapters 4 and 5. This is the last partial exam. And I will drop the lowest grade of the partial exams in the calculation of your final grade. Final exam will cover all chapters. We'll cover all chapters, and will be next week. You should expect what I usually tell my students is the following: 30.
Would the final exam be on a Thursday? The Thursday?
Yeah, Thursday next week. Yeah, it's the last week, right? Here you go. Let's take a look at the schedule here.
What time?
Yeah, here you go. So let me see. 30 exam is the first. Yeah, that's right. So the last day of class is going to be next week, Thursday next week. Right? You can even, let me just get the calendar here to confirm that. It was quick, right? It was only, what, 5 weeks with you? With 300. Academic
What time will the test be? The final.
What did you say?
The final, what time is it at?
Oh, at the same time. Same time, 7:30 to until the end. Or maybe let me think what I'm gonna do. Maybe I'm gonna do a longer exam, you know, and let's see. Since it's a final exam, maybe we might need 2 hours. So let me think. This is the first time I'm teaching this 300 here in such a short, compressed semester. I'm thinking about doing, maybe it might be better to do 2 hours and, you know, before the exam, maybe we review the material. What do you think? Let's do that? Before the final exam, you know, we meet what? We meet at 5 o'clock. We do the exam from, let's see, we'll be here until 8:50. So we do here from 6:50 to 8:50 the exam, and before from 5 to 6:50 we do a quick review of everything. What do you think? So you can refresh your memory. Okay. Now spring session. Let me get here summer session. Here you go. Summer session 1. Summer session 1 to July 9. Okay. July 9. Let's take a look when July 9 ends. Well, oh yeah, July 9 is on Friday. Friday next week. So our last meeting is going to be on the 8th.
Yeah, Professor.
Yeah.
Oh, just wanted to ask you. I just looked on my personal folder,
Yeah.
and I couldn't see any of my graded work.
Really? Let me check. Let me stop recording this thing here and final exam and heat transfer. Let's talk about heat transfer. Four laws of thermodynamics. Okay, 4 laws of thermodynamics. We got that. We talked about also what we talked in chapter 6. We talked about thermal energy. Rising. There are 4 laws of thermodynamics. There is the idea. Oh, we start with the idea. We started with the idea of temperature. Temperature. Then we talked about thermal energy. We talked about the idea of heat. And we talked about the 4 laws of thermodynamics. Okay, so what this chapter is all about? In this chapter, okay, chapter 7, we will discuss how heat is transferred from one place to another. Okay, so what's heat? Heat is transfer of energy. That's what heat is. There is a difference, right, between thermal energy and heat. Thermal energy is what is energy that's intrinsic to an object. It's intrinsic to a system, a microscopic system. It has that energy. A system can acquire energy by being subjected to heat, can acquire more thermal energy by being subjected to heat, which is transfer of energy, okay? So here you go. thermal energy, is energy intrinsic to a system. That's what it is. And it is energy due to temperature, right? Due to temperature, intrinsic to a system. Heat, what's heat? Heat is energy. Heat is the transfer of energy from one place to another. Why am I talking about that again? There's a reason I'm talking about that. We are talking about that, because there are only 3 ways of transferring thermal energy, which is heat, okay? Transferring thermal in the form of heat. There are only 3 ways. That's what we call heat. That's what this chapter is called, heat transfer. You don't have to memorize 300 ways of transferring energy. There are only 3. So, and we are going to discuss that. The easiest one to understand, heat transfer. Heat transfer. There's a very conceptual idea here. We're not going to do much of mathematical problems, but you have to know those ideas. One way to transfer heat is through conduction. Another way is through convection, and another way is through radiation. Conduction, convection, radiation. And I'm going to discuss each one so you understand how they work. The easiest one to understand is conduction. Heat transfer by conduction is heat transfer by conduction. Heat transfer by conduction requires physical contact. Okay, so you have a warm object, an object that is warmer than your hand. You want to transfer heat to this object. What do? You go and touch the object. Let's say my ruler was warmer than my hand and my hand was cold. What do? I touch my hand on the object and we're going to have heat transfer from the ruler to my hand. Okay? Or let's say my hand was too hot and I want to lose heat. What do? I touch my hand in this bottle of water that's cold, and heat is going to transfer from my hand to the bottle of water through conduction. The transfer of heat is gonna be through conduction. It requires a physical contact. That is a very nice way of understanding how it works at the microscopic level. Unfortunately, your book doesn't have here, but yeah, the other book used to have it. You can understand heat transfer. You can understand heat transfer at the microscopic level by imagining electrons moving inside the object. Okay, let me see if I can find my illustration here, so I don't have to draw it from scratch. I had all sorts of illustrations for P300. Must be this one. No, not this one. This one here. No, not this one either. Let me get that here. Must be all the way down here. 300 colleges. Right here. Let's see if it's here. Temperature and heat. Fluid mechanics. Maybe it's this one right in here. If it's not this one, I have to do this drawing from scratch. Oh no, that's not what I want. Too bad. Okay, that's not the one. Okay, I'll have to do that by scratch. You would expand. Okay, so let's close that and let's do the drawing. How it looks like in an illustration way, in illustrative fashion. Here you go, lecture. No, not this one I want. I want this one. This one here. I have some of the drawings here. Here you go. I'm gonna use this one. So here you go. Let's say we have two objects. Okay, and those, what you see right in here is the electrons in a solid object. It can be a metal. Because notice that those electrons, they're moving faster. Okay, because they are moving faster, it's the temperature, the overall temperature of this object is higher than the overall temperature of this one. The arrows of those electrons here are shorter than the arrows of this object here, of these electrons in the other object. Okay, so assume that those are metals, and you have a sea of electrons moving inside it. So if you want to understand conduction, you know, what I'm going to do, I'm going to put this object in contact, in physical contact with the other one. Okay, like that. And what's going to happen? The electrons that are here at this interface are going to exchange momentum with the electrons on the other interface. So let's see, I'm going to put more electrons right in here. Okay, so they're going to collide with each other. Initially, right, this object is colder than the other. That's initially. And at the microscopic level, all those particles, they are interacting with one another. They're colliding with one another. After some time, what's going to happen? The temperature of each of those objects are going to equilibrate. Just like that. I'm going to copy this guy here. Here you go. They're going to reach equilibrium. Here you go. This temperature is the same as this one, and consequently, the speed of those the electron on the right side is going to be a little bit faster than it was before, because they exchanged momentum with the electrons of the other container, of the other object, and the speed of the other object is going to be a little bit shorter, smaller, but would be similar to the speed of the other ones. Okay, so here you go. That's a very good way to visualize how conduction happens at the microscopic level. In the process, you are transferring heat from one object to the other one. Here you go. Okay, here you go. Heat is transferred, here you go. Heat transfer from the warmer object to the colder object. That's conduction. Everybody should be familiar with that because they have experienced conduction all the time, right? Heat flow, we can put like that, heat flow from the left to the right. Heat flow slash transfer due to conduction. Conduction. Like that. Another way to transfer heat is by convection. So let's just update the notes here, right? Conduction. The easiest one to understand is heat transfer by conduction, which requires physical contact. By imagining electrons moving inside each object, inside two different objects. One warmer than the other. The warmer object can be thought as having electrons that are moving faster than the electrons in the colder object. Okay, so here we go. When one object comes in contact with the other, when one object comes in contact with the other, the electrons in the warmer object transfer. Let's see. In the warmer object collides with the electrons of the colder object at their interface, transferring momentum and warming up the object, warming up the colder object. That's how you can have a picture of how this process behaves, how this process works. Okay. Now there's a conduction. Here you go, first one, conduction. Then we have convection. Convection we all experience at home. We all experience convection at home. I used to have a nice picture of convection, but I have to, unfortunately I cannot find it. Okay, so we do observe convection. When we are boiling water in a kettle. So how does it works? You know, how does it work? In the case of convection, warmer molecules naturally moves. No, let's not put naturally. Let's put warmer molecules moves to a colder region. You know, transferring the heat with them. Okay, that is what we call natural convection, and that is what we call forced convection. That is what we call natural convection and forced convection. So let's do the drawing. Here you go. Just imagine a liquid, a boiling liquid. Just imagine water being boiled. Okay, the story goes like that. The story goes like that. First, you know, water in the container is cold, right? And the temperature distribution throughout the container is uniform. That's how you should picture. Then I turn on the oven, the flame on the oven. The flame on the oven. And the water at the bottom of the container starts warming up before the water at the top of the container. Okay? Creating a temperature differential. Okay? Because water molecules at the bottom are warmer than the molecules at the top, comma, they are less dense. Warmer water is less dense than colder water. Okay, so let's do the drawing so you don't just keep on looking at that, right? I'm gonna use this drawing here. Here you go. Here's my container, and I don't need this guy. I don't need this one either, and I'm going to put the level of the water right in here. Right in here. Right in here. Temperature distribution is uniform. Okay, at this point in time, temperature distribution here is uniform. We're going to write that down. Temperature distribution throughout the liquid, uniform temperature distribution throughout the liquid. Here you go. That's at time t equal to 0. Okay, so here you go. A little bit later on, we turn on a flame here at the bottom. Here you go. Let's see if I can get that. Okay, my flame like that, right? Here you go. Ah, I hate that. I don't like this drawing. Let's see if I can get something better than that. Better, right? Okay, here you go. That's the oven, and flame is turned on at the bottom. Flame turned on at the bottom. At the bottom of container. Okay. Warmer. You go. Warmer water at the bottom. Colder water at the top. Like that. So we can say that there is a temperature differential. Here you go. Temperature increase like that, right? Temperature increase. Increase. Okay, like that. Colder at the top, warmer at the bottom. Next, because we have warmer liquid here at the bottom, the molecules of water have a larger volume. So how do we represent them? I'm going to represent them as little spheres here at the bottom. Because they're warmer, they're larger than the molecules at the top. There you go. Water molecules. I'm representing those water molecules right here at the bottom. Higher temperature, they're larger. If you want to make another layer of water molecules, here you go. I'm going to make another layer of water molecules here. But now those water molecules are going to be smaller because they are colder. Their mass is the same, but their volume is different. Okay, so at the top, going further up, here you go. Oh, going further up, even smaller. Group. Let's see if I can get that. Yeah, like that. Here you go. Even smaller. Right? And so on. So this water molecule has the same mass as the this water molecule has the same mass as this one, and the same mass as this one. Okay? So what we say? We say that because they have the same mass, the density of the water molecules, I'm going to put another axis here. Here you go. Density increases, denser upwards. Increase in density. density increase. Okay? This water molecule is less dense than this water molecule, which is less dense than this water molecule. Remember what we saw in fluid dynamics. In fluid dynamics, if you have an object that's less dense than the fluid surrounding it, it tends to buoy up, right? To buoy up. Here you go. That's what happens, right? So now we don't need that anymore. We still have the. So because this water molecule is less dense than this other one, it tends to move upwards. Here you go. I'm gonna put like that. Here you go. Boil up. Oh boy, Jesus. Let's get. Oh, I got it the wrong one. Let's move. You know, those less dense molecules tends to buoy up, to float. Let me get a shorter arrow. Here you go, like that. It is this motion upwards that we call convection. And that's what we call natural convection. Okay, warmer water tends to move upwards, displacing the colder water that moves downwards. Okay. Eventually, you know, when the system is stabilized, what we end up having, what we call a convection current. The case of a convection current is like that. Here you go. How do we draw it? I'm going to erase those waters here, those water molecules. In the case of convection current, you know, you go, warmer water moves upwards. Yeah, I don't like that. Yeah, here you go, like that, better. It's starting to look better, right? Here you go. On this side, on the other side as well, here you go. Here you go, I can see the arrow better. I'm gonna get this guy thicker than that. Yeah, doesn't look good. Yeah, leave this way. Not only we have warmer water moving upwards, we have colder water moving downwards. Like that. Here you go. That's what we call convection current. Move downwards. That's what's happening in our water that's boiling in the oven. Okay? So it's this. What's convection is displacement of heat, is transfer of heat by the motion of mass. We can write that down like that. Convection. Convection is transfer of heat by the motion of a warmer mass. We do observe convection when we are boiling water in a kettle. Because water molecules, so let's finish now. Because water molecules at the bottom are warmer than the molecules at the top, they are less dense. Cold water. Less dense water boils up. Boils up, displacing the more dense, colder water, which sinks. After some time, a convection current is established in which warmer water keeps on moving upwards and colder water moves downwards until the source of heat is withdrawn. That's natural convection. This is natural convection, okay? Natural convection. In forced convection, we use a fan to blow, let's say blow or suck, right? Or suck warmer air somewhere else. Okay? Elsewhere. Not somewhere else, but elsewhere. Okay. In space, because there is no gravity, okay, warmer air does not move upwards like it does here on Earth. Okay? So if you have a computer there in the space station, so if you have a computer in the space station, you cannot rely on natural convection to cool down your equipment. Instead, you have to rely on forced convection. A fan, for instance. So that's what we have about convection. Let's take a look at the internet if you have a nice illustration for convection. convection current. Let's see. Here you go. Yeah, here you go. We have some drawings here. Here's my, yeah, here's the flow of water in a container with water. With container. See, the warmer water is red. The colder water is blue. After some time, this type of motion is sets inside the container, in your water container. Things like that happens in the atmosphere of the Earth and also in the mantle of the Earth. Okay, we have, here you go, we have a convection current here on the mantle of the Earth. The air as well. The air, you know, you can also set up convection current of the air in the atmosphere. Warmer air rises, colder air sinks. Here you go, another one. Warmer air rises, colder air sinks. So those are examples of natural convection. .557 and it's due to convection that we get the breeze from the sea. So if the land, for instance, is warmer than the sea, we do get a breeze from the sea. You know, we set, here you go, we have an interface between, let me get a drawing here. There's a drawing that's in your book, should be in your book as well. If you have land here, you know, I'm gonna do a triangle here. Here you go. Very simple drawing here, no fancy one. Here you go. That's land. Alright. And then we have the water right in here. So let's see. So let's see in the morning. In the morning, no, during daytime, okay? During daytime, the water is colder than the land. So what happens? Colder air sinks here at the sea. It establishes an air current. Here you go. Establishes an air current that circulates from the sea to the land. Okay, and when it reaches the land, because the land is warmer, the air rises up, producing a convection current. So that's why we get the breeze of the sea. During daytime, here you go. During daytime, land warmer than water. We have a convection. We have air convection that produces a breeze, sea breeze. There you go. During daytime, land is warmer than water. Warmer air rises over the land, moves towards the sea, sinks down and move towards, and the colder air moves towards the land, producing the sea breeze. Something like that. During nighttime is the opposite. During nighttime is the opposite. The opposite happens during nighttime. The opposite happens. The water is warmer than the land, and there's a reason for that. Okay, there's a reason for that. Water has more thermal inertia than land. Okay, the water is warmer than the land, and the convection current is on the other direction. Current is established in the other direction. So it's like that. Here you go. Air rises on the sea. Warmer air flows towards the land. It sinks because it's colder here and establish this current. Here you go. Colder, let me put here. Colder on land. Colder on land. Warmer on the water. And you have the exactly the opposite. Here you go. Warmer on land. Colder on the water. What time is that? 6:05. Okay, so let's have a little break now. Let's save that here. It's just very qualitative. Okay, it's very conceptual.
Oh, Professor,
Yeah.
when do you do the attendance?
Oh yeah, good idea. Let's do that. Thank you for reminding.
Oh, okay.
Yeah, thank you for reminding.
Just want to make sure, do I have full points for attendance?
I think so. Let me check. You didn't miss any class, right?
No, so far, no.
Okay. So hang in. And let's see. We did conduction, we did convection, and the last one. Last one is radiation. 3 different ways of transferring heat. And heat, remember, heat is always flowing from the warmer to the colder. Okay, so let's talk about radiation. Radiation is the most difficult one to understand. So here you go. Let's take a look here. Both, here you go. That's a difference between radiation and the other two. Both, the first, let's see, conduction and convection require the existence of particles and masses, particles with masses, for the heat to be transferred. Okay, so in the case of conduction, it's the electrons that transfer the heat, microscopic particles. In the case of convection, should be a larger, larger than electrons. Is the transfer of mass, right? Here you go. Conduction is transfer. In conduction, heat is transferred. Heat is transferred by collision between electrons, warmer electrons and warmer electrons and atoms, between warmer and colder electrons and atoms. It requires particles with mass to accomplish that. In convection, a warmer mass carries heat to a colder region. It also requires something with mass. It also requires something that has mass. Can be, a molecule, a bunch of molecules, like a bunch of molecules, right? Droplets of water, so on. Okay, in radiation, it's a little bit different. That's what distinguished radiation. A bunch of molecules. That's what distinguishes radiation from the other two possible ways. In radiation, the transfer of heat involves no mass at all. Okay? Instead, it involves a massless particle that we call the photon. Or electromagnetic radiation. Here you go. Or electromagnetic radiation. That's another way. The photon particle has no mass whatsoever. No, so what's an example of photon? Okay, photons, you have examples of photons. We have infrared radiation. We have UV radiation. We have light that we can all see. Visible light. We call it visible light. Visible light. But we also can microwave, for instance. Microwave is a type of photon that can transfer heat to a TV dinner. Okay? Microwave, radio waves. In principle, they could transfer heat. Okay? So let's examples. The case of the sun. The temperature, the surface temperature of the sun surface temperature of the sun is higher than this temperature of the earth. Consequently, heat can flow from the sun to earth. That's why we feel warmer when we feel the sun rays in our skin. It's transferring heat. All that light that comes from the sun is transferring heat to its surrounding. And it comes from a place that's warmer. Okay. Another important thing about radiation. Radiation that differs from the other two mechanisms. Radiation, unlike conduction and convection, do not require a medium. In order to transfer heat by convection, we need a fluid. It can be water, can be air. You must have a medium. Convection cannot happen in vacuum. Okay, you cannot set convection currents in vacuum because there is no medium there. The only way to transfer energies through the vacuum is by radiation. Conduction too, you need a medium. You need a piece of metal that's warm to go touch, for instance, a piece of metal, right? Doesn't have to be necessarily metal, but can be an object that you're going to touch. You need a medium to transfer that heat from the warmer object to your hand, for instance. But in the case of radiation, no, there is no need. So radiation is kind of unique. It's a unique way of transferring heat from one place to another. It doesn't involve particles that has mass. It doesn't involve, does not require, it's not that it does not happen in a medium. It does not require a medium. Okay, it does not require. Doesn't mean that it will not transfer through a medium. Yes, it does transfer through a medium, but it does not require. Radiation does not require a medium to transfer heat. Is at a higher temperature, the temperature of the sun than the earth, right? Heat can flow from the sun to the earth. The only way that heat can be transferred from the sun is by radiation, because there is no medium in between the earth and the sun. Okay, we do not have a gigantic piece of metal connecting the sun to the earth in space. We don't have it. No. Okay, if you could set up a gigantic piece of metal that's very long, touching the surface of the sun and touching the surface of the earth, we could transfer heat from the sun to the earth by convection. We could, but that's not practical. That metal would be much larger than the earth, wouldn't have any, there would be no way for us to do that. Okay, so the only way that we can do is by radiation. So those are the three different ways that we have to transfer heat. Remember, three, right? There's not difficult to remember that, to memorize that. It's only three: conduction, convection, and radiation. Okay, that's in my book, the 7.1, 7.2, and 7.3. All these three in my book are in sections 7.1, 7.2, and 7.3. Okay, so we are not going to cover, skip 7.4 and 7.5. That's in my book, okay? I do not know how your book there. But we are going to do heat transfer and phase and change of phase. Okay, that's an interesting topic here. It's rather simple to understand as well. I remember learning about that stuff back in Brazil when I was in elementary school there. I believe it was my third year in school, third year of elementary school there. The professor would draw some graphs there in the board. I would memorize it, but I didn't have a clue what that means. Okay? I wonder if you have seen that before. Most likely you have seen. Okay, heat transfer and change of phase. Let's first talk about change of phase. Phase of matter. Phase of matter. There are three types of phases. The matter has three types. Matter has three types. There are more, but for the sake of this course, just stick to three. Okay? Matter has three types of phases: solid, liquid, and gaseous. Okay, that's solid, liquid, and gaseous. Gaseous. Okay. That was the phase of matter. And we can have a change of phase. A given substance can change its phase. The most familiar to you is water. You can have solid water in the fridge, in the refrigerator. Let's say for solid water in the freezer. Let's put the freezer instead, right? You can have liquid water at room temperature. And you can have water vapor. Now let's see, gases. Let's put steam. We can have steam when you boil your water. Okay, you can have. Here you go. Solid water in the freezer, liquid water at room temperature, and steam when you boil your water. That's the most familiar to you. Three different phases. Solid, liquid, and gaseous, okay? And we can have change of phases from solid to liquid, from liquid to steam. That happens not just to water, but it happens to other substances there as well, okay? These different phases occurs not just to water, but to other different substances. You can have liquid iron. Yeah, you can have. If you heat it up hot enough, it's going to melt. Your iron is going to melt. That's possible. Okay. And we're going to study that. There is a very interesting behavior when there is a change of phase of a given substance. That was that graph that I learned in elementary school there in Brazil, which I never, for a long time, I didn't understand very well until I came here to the United States and started to perform experiments. It's a very interesting situation, okay? So here you go. I'm going to show this graph to you. You're gonna get this arrow here. In this graph, we plot the temperature against the heat, temperature of the substance, the phase diagram we call it. It's, for some reason it's not in your book, unfortunately, but I want you folks to understand that. Here you go, there's a temperature here, degree C for instance. Superscript. And amount of heat. Remember, heat is energy, transfer of energy, and the unit is joules. There is a very nice experiment that we can do, and I did that at a community college. I saw that for the first time. Okay, phase diagram. Here you go. So let's say 0 degrees is somewhere around here. Okay, let's say 0 degrees is somewhere around here. I need space, so I'm going to put my 0 degrees a little bit higher. Here you go. Zero, right in here. And what I have, you know, you have a given instant of time, you have a solid ice, a cube of ice. And in order for you to have a cube of ice, the temperature of your ice must be below 0, okay? And what we are going to do, this experiment is like that. We get a cube of ice, and we start to warm it up. We start to warm it up. We apply heat. Here you go. Get a cube of ice, put in a container, take your container to the oven, and start to warm it up. Turn on the oven. What's going to happen to that cube of ice? It's not going to melt instantaneously. It's not going to melt instantaneously. Okay? It's going to increase its temperature little by little. If it was initially at minus 20 degrees C, okay? So its temperature is going to increase up to a certain point. And increases linearly, by the way. We are using an oven that is outputting a constant rate of heat. Okay, a constant rate. You don't have a high loss of heat being output and then you decrease. No. It's the same level of heat in your oven all the time. If you do that, you're going to have a linear increase on the temperature of the water, like that. Okay, when the water, the solid ice reaches 0 degrees, something interesting happens. Okay? Which was something I didn't understand at that time when I was taking this class there in Brazil, in elementary school. Something interesting is going to happen. Even though you're warming up your ice cube, at 0 degree, the temperature of the ice cube remains the same. Okay? The temperature remains the same. Let me put a little bit steeper. Here you go. Now we have it here. In this region, here you go. In this region right in here, we have only solid nothing but solid in this region. Okay, so he go from here to here. Oops. Solid. You go. Until it reaches 0 degrees. It's only solid water, an ice cube. I keep warming up my substance, the temperature doesn't change. But something else happens. You have a mixture of solid and liquid at this point at 0 degrees. Mixture of solid and liquid. Okay? Until you melt all the ice. And you require, and there is some heat. We can predict how much heat you need to do that. So, and the amount of heat to do that, to change completely the phase of the solid water to liquid, can be, depends on the mass of the water. Depends on the mass of the ice cube. In the next step, when you completely melt all the ice, what happens? Then you are going to have an increase in temperature again. Okay, so here you go. The slope is going to be a little bit different, but for the sake of this course, I'm going to put almost the same one. At this point right in here, in the next part of this diagram, you have only liquid. Liquid only. Only liquid. Okay, I need to make it a little bit shorter. Here you go. You can make a drawing as well. This is a phenomenon that can be done at home, okay? All you need is a thermometer to track down the temperature of your water. We did that at community college. To track down the thermometer, to track down the temperature of the ice, the temperature of the mixture of solid and liquid, which is going to end up happening at 0 degrees C. The temperature of the liquid after it was the ice was completely melted. And then when it gets to the point where you have 100 degrees C, around here, the same thing happened. We're going to have a change of phase again. Change of phase here, change of phase, and behaves exactly the same way. You're going to have a mixture of liquid and gas, liquid and steam, gas, and liquid. When the liquid is going to be converted into gas mixture. Go, get it here. We can also calculate the amount of energy required to convert a liquid into a gas. Liquid and gas. And the amount of energy required to do that depends on the mass, on the initial mass of the liquid. When you boiled completely your liquid, then the temperature can increase again. Okay? Here you go. So energy in this case is being used. Heat, right? Heat in this case. And the energy transfer, that is the energy that's being transferred to the substance, is being used not only to increase the temperature of the substance, but also to change the phase of the substance. That's what this energy is being used for. It's being used for the two things. Okay? Make sense? Okay, this is an experiment that can be done fairly easily. The only problem is to perform this experiment here in this region. You know, to keep the steam in a given container is very difficult. It's very difficult. You can perform the experiment up to this point. From this point on, it's very difficult to contain the steam in a container. Require high pressure. Okay, it's just like your pressure cook. It's not gonna, be easy to do this part of the experiment. But up to here, yeah, you can. And then here you go. Here's just gas, just steam. Here you go. I'm gonna get this guy right in here. Only liquid. Liquid and gas. Move up. And steam. So notice that we're using energy in the form of heat to change the temperature, not only to change the temperature, but also to change the phase of the substance. Okay? This graph is very easy to memorize, right? It tells you a bunch of things in a very easy way to memorize it. Let's document what we have here. Okay. Okay, to that we have what we call a phase diagram to illustrate what happens to a substance when we can use, here you go, we can use a phase diagram. What happens to a substance when we add heat to the substance? Okay. In the vertical axis, we document the temperature of the substance. In the horizontal axis, we document the heat applied to the substance. This heat, the energy from the heat is used both to increase the temperature of the substance and to change its phase from solid to liquid and from liquid to gas. That is the melting point, which is the temperature required to turn solid into liquid. Melting point of water. Melting point of water is 0 degrees C. At this temperature, you have a mixture of solid and liquid water. When water reaches this temperature, the substance, well, let's see, when the substance, not water, but when the substance reaches its melting temperature, at which, not required, but at which solid turns into liquid. Okay, below this temperature, you have only and liquid substance, a mixture. Okay, below this temperature, you have only solid substance. It doesn't have to be water necessarily. It can be any other substance. So there is the melting point, which is the temperature at which solid turns into, which solid starts to turn into liquid. Here you go. Melting point of water is 0 degrees C. At this temperature, you have a mixture of solid and liquid. Below this temperature, you have only a solid substance. When the, when the temperature, when the substance is in its solid state and heat is applied, its temperature increases. However, when the temperature reaches the melting point of the substance, of the substance, its temperature does not change at all and remain constant until all the substance is melted. Okay, here we go. At this point, this solid turns completely into liquid, and its temperature starts to increase until its boiling point, when again the temperature remains the same. Temperature remains the same until all the liquid changes its phase to gas. Okay, that's what description, what this phase diagram is all about. So that, notice that we do require some energy to change the phase of the substance. Okay, there's a amount of heat that we must apply to change the phase of the substance. And that's what 7.9 in your book is. Okay, so that's what we have for this chapter. Chapter 7, it's 7 o'clock right now, right? Any questions? We're going to be here another 2 hours, almost 2 hours. And I want to start electricity. Electricity is lots of fun. I like electricity. I didn't like electricity when I was going through undergraduate school. And today but today I like it. I didn't pay much attention to electricity. So, any questions? Let's take a look at the homework of this chapter. Here you go, homework folder. That's 7. Let's take a look at homework 6 and 7 before we go into the next one. Here you go, homework 7. See, problems on conduction. Here is, that's temperature, okay? When an object is warmer or is at a higher temperature, what does it have to do? It has to do with the molecular kinetic energy. Remember, it has to do with the velocity of the molecules in the substance, right? So, and the temperature is mostly due to the translational motion of the molecules, not the vibrational, not the rotational. It's all written there in the book. But that's rotational, right? And vibrational means when the molecules is vibrating like that. But the temperature has to do with the motion, translational motion of the molecule. And we have other things here, temperature of boiling water. You can make a change here from 100 to Fahrenheit to see if they're the same or not. Or the temperature of melting ice. What's the unit of heat? Which unit do we use? Oh, by the way, heat can be used. We can measure heat both in joules and calories. Okay, calories is just another way of measuring energy. Just another unit to measure energy. Keep that in mind. There is 1 calorie is like 4 joules, more or less. And what happens if you add some heat to 1 liter of water and 2 liters of water? Which one is going to have a greater change in temperature? Okay, the larger the amount of water, the more heat you're going to need to warm this one here to the same temperature as the other one, okay? Remember I told you that? Okay, here you go. And let's see. That would be number 6, right? You have to turn in. Which one do you have to turn in today? That's 4 and 5. You should have to turn in today. This one, number 6. Let's turn it in. Yeah, let's turn it. We finished number 6 last week, right? Thermal energy. Yeah. Yeah, let's turn it in on next class meeting, which is, yeah, homework here. Homework chapter 6. Okay, do homework 6. Do. Okay, and here. Let me see here. Someone is. Good. So we just finished chapter 7, and let's make it do on the last day of class. I'm not sure if we'll be able to cover that. Okay, so let's see, 6. Okay, we are meeting on the 6th. Okay, good. So let's see. We should plan for electricity here and magnetism here. Let's plan like that. Electricity chapter 8 and magnetism chapter 9. That would be on Tuesday. And homework 7 do. Chapter 7. Here's going to be chapter 6. Chapter 9. Final exam, we're going to have review, homework 8. I'll have to prepare homework 8 and 9 for you. Okay? That's all depends how much we cover here on chapter 9. Homework 8 definitely. And then we have final exam. Went fast, right? One person here. Good.
Professor, I have a quick question.
Go ahead.
Since we're turning in today, homework 4 and 5, is there any way that you can grade those before our exam on this Thursday so that we can have that to study from?
Sure.
Okay, yeah, I would really appreciate that.
Yeah, I did that, I can do that.
Okay. Thank you.
4 and 5, and yeah. I'll do everything this weekend. Or maybe even before. Tomorrow. See, you're turning in what, before midnight, right? So I have to wait until midnight before I start correcting. After midnight before I start correcting, okay? So electricity. Any other questions? So let's start with electricity. Electricity.
Professor?
Yeah.
Oh, what day was the homework 7 for July 8 and 9? What homework was that?
Let's see here. July 8th.
July 8. Okay,
Yeah,
thank you.
July 8th is Thursday, yes. July 8th is Thursday. Homework 8 and 9 do. Okay. And I'm gonna save as version 3. I'm going to save as PDF as well. Okay, and let's talk about the electricity. Our last break was 6:20, right? Yeah, 6:25. Let's go another. Let's see, break Newton. Yeah, let's go until 6:30, 7:30. 7:30, 7:45. That's good. Yeah, let's do like that. 7:30 is electricity. What do you have to know about electricity? What do you have to know about it? Let's go back to our. We have now to revisit the basic quantities again, because now I'm going to introduce you to a new concept, to a new idea, to a new quantity. Here you go. I already introduced you to the temperature, the concept, the idea of temperature. We're not going to talk about that, so let me put here. But what we're going to talk about is this one here. That's the one we're going to talk about. We're going to talk about the electric charge. It's a concept that was created to understand electrical phenomena, not just electrical phenomena, but also magnetic phenomena as well. And then you already told you about the 4 laws of thermodynamics, right? But there will be also 4 laws of electricity and magnetism. I see which one. Hopefully we'll be able to cover everyone. So you gotta have this picture of an electric charge. In electricity, we have a basic quantity that you must picture in your mind. It is called the electric charge. Okay? Every matter can display. Every matter has these electric charges. Okay, and there are two charges. Actually there are 3 types of charges. 3 types of charges. One is the negative charge, represented by the electron. The other is the positive charge, represented by the proton. And then you have a neutral charge that represented by a particle that we call a neutron. So there is negative, positive, and neutral charge, electric charges. And neutral electric charge, we represent those charges just by little circles. Every battery is made up of those charges. So let's see my positive charge. I represent it by the positive sign. Go. My negative charge I represent by this negative sign. I see a little circle with a negative sign, and then we have the neutral charge that's represented by the number 0. And we do have particles that are just positive, particles that are just negative, and particles that are neutral. Those particles are the proton, the electron, and the neutron. The electron was discovered at the end of the 1800s. The proton later on, and the neutron later on too. You can go to the Wikipedia to find out those things. Here you go. When was the electron discovered? Let's start with the electron, because it's just the discovery of the electron. Here you go. It didn't happen right away. Those. Here you go. 1897, almost at the turn of the century. Almost the turn of the 19th to the 20th century. J.J. Thomson. It is a very interesting story, okay? in 1850, scientists had invented a device, very important device. This one that you see right in here is the cathode ray tube. Okay? They invented, but they didn't understand very well how this device worked. You know, think about that. You invent this thing in 1850, you start playing with it, performing experiments, and they start to see things in this device that they could not explain. It was only like 40, 50 years later that they found out that, I'm going to show you, here you go, an illustration. This one right in here. See? That we call the cathode ray tube. We have those things at community colleges, at the community college that I work. So it's an evacuated tube that you can apply a high voltage between two electrodes right in here. And we have a plate, a little plate. Let's see if I can show that to you. Yeah, this one right in here. Here you go. That's terrible. Okay, better. Okay. We apply a high voltage between this plate here and this other plate. You can put a battery, high voltage battery. Okay. So these devices, you know, before the discovery of the electron, they observed that they would emit some sort of rays from one end to another. This ray here could be visualized if you put some gases there inside. It was like greenish color like that. People were seeing that and they didn't know what this ray was all about. They would call it a cathode ray. That's what they would call it. Let me get another one. We're looking. Well, let's stick to this one. Yeah. They would apply a high voltage here. They would put some gases. That's one way of doing that. It's not exactly. It's just not. They would put very little gas. They wouldn't put a lot of gas in there. The pressure was much smaller than outside the tube. It was just enough that, but the concentration of gas was just enough to produce this fluorescence that you see here, that they would call a cathode ray. They didn't have a clue what this thing was all about. Until that 50 years later, J.J. Thomson theorized that this rays that he saw here was in reality a particle, a new type of particle, an elementary particle that they call the electron. 1897, when he discovered the existence of electron. Okay. And what about later on? Later on, people discovered something else called the proton. Discovery of the proton. Let's see, I want to see this one here. And let's go to proton, Wikipedia. Let's go to Wikipedia. The proton was discovered by this guy in 1920, Ernest Rutherford. Okay. A positively charged particle. And then we discovered the proton 1920. And what about discovery of the neutron? Neutron was a little bit later. (1932) by James Chadwick. Okay, so here you go, electron discovered in 1897 by J.J. Thomson. Proton discovered in what? 1920, right? That's good. By Ernest Rutherford. Rutherford. Proton, here we go. Ernest Rutherford. And then you have the neutron by James Chadwick, 1932. Neutron, discovered in 1932 by James Chadwick. Okay, so it was from these particles that we created a model of our atom, Okay, what we know today about the atom? We know that atoms are formed by those three particles. And a very good model of the atom is the one that has a nucleus, a very small nucleus, it's not that big, and electrons orbiting. You learned that in chemistry, right? Go. No outline, I want here. No fill. No fill. Go. Go. Inside the nucleus of the atom, we have protons and neutrons. That's a very good model of the atom. Protons and neutrons. Surrounding the atom, we can say orbiting the atom, we have electrons. The number of protons and electrons depends on the atom. The number of protons, electrons, and neutrons depend on the atom. That's, I want to make it a little bit smaller here. Okay. Like that, atom. Atom. Okay, 7:25 right now. Let's take a little break and we continue. Break from 7:25 to 7:40 p.m. and then we can go all the way down to 8:50. Any questions? Okay, so I'll see you in 15 minutes. I can't unmute. You can't unmute? Okay. So let me see here. Yeah, try to unmute there, Blaze. You should be able to do that on your own, okay? Okay, here you go. Now you're muted. You can talk. Yeah, I cannot hear you, anything. I cannot hear you. Looks like you have a problem with your mic. Yeah, if you need to talk to me, just send me a chat message, okay? I cannot hear you. Let me see here. We have a problem. Well, let's have a break and I'll be back in 15 minutes. You should type. too. Gotta turn on my recording. Here you go. So those three particles makes up an atom. An atom is has a nucleus. Has a nucleus. Has a nucleus and a cloud. We say a cloud of electrons orbiting the nucleus. In the nucleus, we have protons and neutrons. The nucleus is very small compared to the size of the atom, compared to the size, to the orbit of the electrons. Very small. Now what else you gotta know? Every matter is made of atoms. It's made of atoms. There are more than 150 non-atoms. Non-atoms. Each of these atoms have a different number of protons in their nuclei. Okay, that those atoms are documented in the periodic table. Periodic table. Okay, let's take a look at the periodic table. We have already seen that in chemistry, right? So periodic table. Periodic table of elements. Here you go. Each one of those squares here is an element, is an atom. An atom with one proton in the nucleus. This is an atom with two protons three protons in the nucleus. Hydrogen has one proton. Helium has two. Lithium has three. Beryllium has four, and so on. Okay? And matter is made of a combination of different atoms. We are made mostly of carbon, oxygen, nitrogen, and hydrogen. Organic matter is made mostly of carbon, hydrogen, oxygen, and nitrogen. And their models are exactly the same. The only difference is the quantity of protons in the nucleus and how many electrons orbit the atom. The quantity of protons and neutrons in the nucleus and how many electrons orbit the atom. But their basic model is that: is protons and neutrons in the nucleus and electrons orbiting the nucleus. The only thing that changes is the number of those particles. And what gives the chemical property to the atoms is the number of protons in the nucleus, okay? So we have how many here? I want to see exactly the number of. Here you go. I see here 103. Okay, it's not 150. No, there's more. 130. I thought it was around 150, but it's not. It's 118. Yeah. Let's see. Let's take a look. Every now and then they discover a new element. Oh, that's Portuguese. You don't want Portuguese. Let's go to the English. Periodic table, Wikipedia.
Oh, Professor, I have a question.
Yeah, go ahead.
Okay, so are there any homeworks that are due on Thursday?
Let's take a look at the syllabus here. This coming Thursday, homework 4 and 5. Wait a minute. No, homework 4 and 5 is today. This coming Thursday is homework 6. Here you go. Okay?
Okay.
Homework 7
And
on
will
Tuesday.
stuff from homework 6, will stuff from homework 6 be on exam 3, or was it just homeworks 4 and 5 for exam 3?
Let me see what I did. Oh, here you go. It's written down here. Third exam, chapters 4 and 5, homework 4 and 5. Okay? Chapters 4 and 5 correspond to homework 4 and 5. Homework 4 and 5. Okay?
Okay.
Exam 1 was homework 1 and 2, right? Exam 1, let's see. Where is exam 1? Homework 1. First exam, homework 1 and 2, chapters 1 and 2. Second exam, homework 3. And third exam, 4 and 5. And then the final is going to be everything. Final exam is going to be everything. And you should expect, you know, some 1, 2, 3, 4, 5, 6, 7, 8. Maybe, you know, you should expect like 50% of what was covered in the previous exam and 50% what was not covered, something like that. Okay? Final exam, expect, you know, expect 50% of the material, of the material that was not covered. Okay, that's okay. I'm gonna mute you, Blaze, because there's too much noise there on your side. Okay, good, thank you. So let's go move forward here, and yeah, 118. It's not 150. It's 118 elements. But every now and then they discover a new one. So let's correct that here. 118 atoms. Each of these atoms have a different number of protons in their nuclei. Every now and then, we discover a new atom. What else you have to know? Okay, you have to know how the positive and negative charges, how they behave. Okay, you have to know about the first law of electricity and magnetism. It is the Coulomb's law. We call it the Coulomb's law. What does the Coulomb's law says? The Coulomb's law says the following. If you have one positive charge next to a negative charge, okay, they interact with one another. Just like the masses, they attract each other. Positive and negative charges, they also attract each other. There you go. Attractive force. Okay, here you go. Force of 1 in 2, force of 2 in 1. That's part of Coulomb's law. You have to memorize that. And then if we have two positive charges, now that's where things change, you know? They repel one another. And if you have two negative charges, they also repel each other. There you go. What else? Coulomb's law, So positive and negative charges attract each other. Positive and positive charges repel one another. Negative and negative charges repel one another. Here you go. What else? We can also say that positive and neutral, the force between positive and neutral charges is 0. That's similarly the force between a negative and a neutral charge is 0. Similarly, the force between a negative and a neutral charge is also 0. So if you put a charge next, whether it's positive or negative, next to a neutral charge, there will be no force whatsoever. A proton, doesn't attract or repel a neutron. Similarly, an electron doesn't attract or repel a neutron. Here you go. 0 force. Force is 0. Force is 0. That's what we call electrostatic force. Electrostatic force. Here too. When I mean force, we call it electrical force or electrostatic force. Electrical or electrostatic force. Electrostatic force. In this case, positive and negative charges, they are not 0. Can be either repulsive or attractive. So now we have Coulomb's law. Let's write that down here. There are 4, okay, but let's put it one by one. Coulomb's law. What else do you have to know about Coulomb's law? You have to know that Coulomb's law has a format that's very similar to the law of universal gravitation. Here you go. The force is something like that. Here you go. Oh, by the way, before we go into that, here you go. Before we go into the force, I gotta write down something else too. We can also quantify the value of a given electric charge. Okay, an electron a given charge in terms of the unit of Coulomb. Okay, so an electron, for instance, as a charge. What's the value of the charge of the electron? I never memorize. You don't need to memorize either. Okay. I'm gonna give that to you. It's 1.6 times 10 to minus 19 coulombs. Charge, we denote the charge by the letter E, minus 1.6 times 10 to minus 19 coulombs. That's the charge of the electron. And the charge of the proton, you know, a proton has an electric charge given by P, you know, it's also given by E. Well, we call it P, but instead of negative, it's going to be positive. It's the same value as the charge of the electron. And a neutron has an electric charge equal to 0. Has no charge whatsoever. So we put 0 here. Here you go. Like that. 0 coulomb. And the force that you saw here depends on the charge of the particle. You know, you have particles that can have a bunch of electrons, has an excess of the electrons, it's going to have, you know, an electric charge that's going to be the number of electrons times the charge of the electrons. Okay? So here you go. I give an object, the charge, here you go, the charge of a given object is the charge due to the number of excess electrons or excess protons. Okay? An object that is negative, that has a negative charge, has more electrons than protons. An object that has a positive charge has more protons than electrons. In general, matter at the surface of the Earth has a neutral charge. In general, here on the surface of the Earth, neutral charge. In general, object has a 0 charge. This pen right now most likely has a 0 electric charge. But I can electrically charge this pen just by rubbing it against my hair. It's possible to do that. Okay, that's one possible way of electrically charge an object. Now, let's go for the mathematical equation for Coulomb's law. You already know how attraction and repulsion of electric charges is part of Coulomb's law. Now let's look for the mathematical equation of Coulomb's law. Coulomb's law. Well, Coulomb's law is very similar to the Newton's law of universal gravitation. Coulomb's law, the electric force, goes down to the square of the distance as well, just like the gravitational force. Okay, I'm going to put like that. Here you go. Electric force, I'm going to put like a subscript E, just to differentiate it from the gravitational force. I'm going to put a little g here for gravitational force. I'm going to put little e for the electrical force. Okay? They both goes down as the square of the distance. In the case of the electric force depends on the electric charge, Q1 and Q2. just like in the gravitational law. The gravitational force depends on the masses, m1 and m2. Remember that the gravitational force is also proportional to this constant, universal constant that was measured, that we call the constant G. In the electric case, we also have a constant, but the constant we give it a name with the letter K. There's a name for that constant. Easy to remember, right? There's a value for this constant K. I'm going to write that down here. K is equal to 9 times 10 to the 9 Newton meter square divided by Coulomb square. Superscript. There you go. That's the unit of this constant K. It's lowercase k, okay? Remember that big G is different, right? Big G is a much, by the way, is a much smaller number, big G. Like that. The units are different, 6.67. 67 times 10 to minus 11. Minus 11. The units are different. Is instead of Coulomb square, is going to be kilogram square downstairs. This number is much smaller than this number here. Okay. So two different forces. One due to the mass of a particle, the other due to the electric charge of a particle. Okay. What else do you have to know? At the microscopic level, the electrical force is much larger than the gravitational force. Gravitational force. We say that the electrical force rules supreme in the microscopic world. Microscopic world. What else can we say? We say that also the gravity. Well, we also say that the gravitational force between particles, gravitational force at the microscopic level, is negligible. So if you're going to study atoms in physics, you do not have to worry about this force. You worry only about this force here, the electrical force. And the model of the atom and the planet is similar, right? In the case of the solar system, you have the sun at the center of the solar system and the planet revolving around the sun. In the case of the atom, you have the nucleus of the atom with the electrons revolving around the nucleus. So that's the planetary model of the atom, we call it. Okay, so here we go. What else we need to talk about? We talked about charges. Okay, that's one of the basic quantities in physics. If you don't believe in the existence of electric charge, you cannot understand electricity. You cannot understand electricity and atoms, and you cannot understand atoms, and you cannot understand atoms. We talked about charges. Okay. Charges can produce electric forces. And that's one, Coulomb's law, one of the laws of electricity. What else do you have to know? You may have matter that is electrically polarized. What does it mean? Okay, we can have something like that. Okay, let me show you exactly what I mean by that. You can have objects that has a neutral charge. Here you go. You can have an object. Here you go. Let me draw the most generic object here. Here you go, like that. You can have an object that have electric positive and negative charges that are so close to one another that the object is considered neutral. Okay? But you can also manage to separate those electric charges in the same object. You can have something like that. Most of the time, the object is going to be like that. The electric charges are going to be the positive and negative charges are going to be very close to one another. The net charge is still zero because the positive cancels with the negative. Net charge zero, object neutral. Here you go. Net charge zero, object has neutral charge. In this case, charge is negative and in this case, negative and positive charges are very close to each other. Okay. Very close to one another. But then you can also have a case in which you have more positive charges than negative charges. Okay, here you go. we have an excess of positive charges. I'm eliminating the negative charges here. Object with excess. Object with excess of positive charges. It is positively charged, positively charged. Okay. And you can have the other way too. We can have an object with excess of negative charges. There you go. I'm going to excess of negative charges. I have to, remove some positive charges here. Objects with excess of negative charges. We say that it's negatively charged. Neutral, net charge 0. Negatively charged, positively charged. And then we have something else too. We can have an object that's neutrally charged, but with one important distinction. The charges, the positive and negative charges, are separated. Okay, so I have here 1, 2, 3, 4, 5, 6, 7, 8 negative charges on one side. And we can have oops, 4, 8 on the other side. We say that this object is polarized. Here you go. It's better described like that on one side here. Let's go. Here you go. It's possible to get an object like that. Here you go. This type of object has a net charge equal to 0, but we say that it is polarized. Just like we have a political polarization, right? We say that we also have charge polarization. Here you go. Like that. I should put negatives throughout here. It's going to be a little bit more difficult to draw negatives. Let's see if I can do that. Make it look better. Yeah, for some reason I cannot do that with that negative. I don't know why. Okay. Going to be lots of work, but you got the idea, right? That's what another type of charge distribution. Here you go. Objects that are polarized like that, they can also be attracted by electric charges. Here you go. We do have, here you go. I can have attracted or repelled. I can have, for instance, a negative charge right here, attracting this object. Here you go. Outline. Here you go. We can have electric force between, because these positive charges are closer than the negative charges. Okay? And we are going to end up having an attraction between those two objects. It's possible. If I put a positive charge, we're going to have a repulsion between those two objects. So you can have something like that, and we do observe that. 820, almost there. So here you go. We have electric charge. Electric charge. We have electric force. We have electric polarization. Okay? And now we have something else. Something else that's introduced in the book that's called electric field. Lots of concepts here. The main concept, the core concept is this one here. At the top of that, that's the main concept. You need this concept to see what an electric force is, to understand what electric force is. You need this concept to understand what electric polarization is. And you also need this concept here, together with this one, to understand what an electric field is. The way I like to define an electric field is in the following way. I'm going to write that down. What is an electric field? What is an electric field? Okay? First I'm going to illustrate it, and then I'm going to formalize its definition. I'm going to get two charges here. Here you go. Two electric charges. Okay. The negative charge is attracted by the positive charge. I'm going to eliminate this one because what matters is what you see right in here. Oh, wait a minute. No, I'm going to go all the way around. All the way around. Okay? So I'm going to eliminate this one here. Okay? So this positive charge is being attracted by the negative charge. Okay? If the charge is in there, we have a force. And I represent this force by the letter F. Okay, here you go. Now, I remove this charge. What happens? There is no force anymore, right? There is no force anymore. But something else is left behind. Well, this force here is no longer there. I'm going to put it just like a little ghost. But something else is left behind. This something else is called an electric field. Here you go. I'm going to put it in red color. Like that. Here you go. Red color. And this electric field is not zero. Like that. Here you go. Tell you the story. An electric charge is next to a positive charge is next to a negative charge. There is an electric force. If we remove the charge, and I'm going to illustrate this removal by, I'm going to put this one, here you go. I'm going to illustrate this removal by dashing, not this one, I remove the charge, the force becomes zero. Okay? However, where the charge was located, there is no more force. There is no force anymore. Something else replaces the force. This something else that's always there, that is always in there, is called the electric field. Okay, here you go. Like that. In the next slide, I remove this guy completely. So that's the illustration, the graphical way of understanding the electric field. If I'm going to do it for the positive charge, let's say 2 positive charges now. This one is a positive charge. The force is going to be on the other direction. You go. Like that. Okay, we remove the positive charge. And the force becomes 0. There is just this ghost of the charge in there, no force whatsoever, but something else is replaced in there. Something else replaced the charge. The charge is no longer there. The force is 0, but there is something else that is always there, whether you have a charge or not, which is the ability of the charge to exert a force. That's the electric field. Go. Electric field. Like that. What is the electric field? Now I'm going to define it in a more. What's an electric field? It is the ability that an electric charge has to exert an electric force in space in case a charge is placed, and a second charge, in case a second charge is placed at that spot. It's the ability Can you picture that? Okay. Positive charges, electric fields. What do you have to know? Electric fields point away from a positive charge. Electric fields point towards a negative charge. That's what you have to know. Go. Positive charge, electric field pointing away. Negative charge, electric field pointing towards the electric charge. For a point charge, we can map. We can map this electric field for a point charge. You go. Let's do it. Negative charge. You go. You go. Like that. Electric fields pointing towards the negative charge. This is a very, Seeing is a very abstract concept. Okay? We can have, that's the one you must know. A point charge is the easiest one to understand. The other one's a little bit more complicated. Your book have different charges distribution here, but this one you must know. electric field lines pointing towards the charge. You go positive charge, electric fields pointing away of the charge. You go. Here you go. Negative charge, positive charge. It's in your book. What time is that? 8:30. We can go further. Well, you know what? Let's do some. Do we need any help with the current homework? If you keep on doing that, it's gonna become too tiresome, right? Let's. Do we need help with the homework? Either today's homework or future homework? 20 more minutes to go.
Yes, Professor. I just put down my homework for 4 and 5. Do you have it?
Let me check. Let's see here. Homework 4 and 5. I see it. Yeah, it's right in here. I can see it. Good. Let's press a little bit some of the questions in the homework for the electric field. So the electricity. So you know what to do. That's gonna be number 8, right in here. Oh yeah, here you go. I'm not gonna do everything. I'm gonna do just one or another. Okay. Okay. The nucleus of an atom is charged what? Go ahead. Answer there in the chat box for me. Give me your answer in the chat box. Of course, private, right? So nobody else sees it. Anybody else? Raquel has answered her question. You have negatively charged, positively charged, both negatively and positively charged, none of the above. Okay. And remember, they put only negative and positive, right? The nucleus, and he said the nucleus of the atom. The nucleus of the atom. Just go back to the model of the atom, how it is. Okay, well, the answer is the nucleus of the atom is positively charged only. You have positive charges and you have neutral charges. So you do not have positive and negative in the nucleus, okay? You have only positively charged, so that would be the right answer. The electric charge of all electrons are identical. It doesn't vary from ion to ion, doesn't vary from atom to atom. So that's the beauty about this model of the universe, this model of atoms. Atoms are made of electrons, protons, and neutrons, and the electrons do not change from atom to atom. They are identical. Okay. Oh, I gotta tell you about the mass of the proton as well. Okay. I didn't tell you about the mass of the proton. Let's talk about it. If you go in your book, at the very beginning of your book, they usually have a table here. My book has a table here. Okay. Not only, here you go. Remember that we have that basic property, basic quantity, length, time, mass, temperature, and electric charge so far, right? Okay, so a given particle, the electron, for instance, it has an electric charge. It's a negative electric charge. And because it is a particle, it also has a mass. Okay? Those two properties are different, independent of one another. So the question is, It's very important for you to remember that. It's a very important piece of knowledge. What's the mass of the proton compared to the mass of the electron? Okay? So I'm going to write that down here for you. Here you go. You already know that the charge of the proton is the magnitude. You know that the magnitude of the charge of the proton is the same as the magnitude of the charge of the electron. Okay, you already know that. Let's take a look. Here you go. Here you go. Take a look. Magnitude of this charge is the same for the proton. It's just the sign that's different. For the electron is negative. You already know that. Okay? What you do not know is the mass. The magnitude of the charge of electron, let's put here, is the same as the charge of the proton. Charge of the proton. You already know that. What you do not know is the mass of these two particles. Okay, that you do not know. You do not know the mass of these two particles. Well, we have measured the mass of those two particles. You do not have to know the exact value, numerical value, but you have to know one important piece of information. Okay, the mass of the electron, I'm going to write that down here, the value of the mass of the electron. Like I said, you don't need to memorize this number, but you have to memorize something simpler than the number. I'm going to put it here, mass of the electron. It's in your book. Okay. It is in kilograms, 9.1 times 10 to minus 31 kilograms. It was measured, okay, times 10 to minus 31 kilograms. That's the mass of the electron. Okay, now I'm gonna write down the mass of the proton. Mass of the proton, here you go. You don't need to put that negative sign there, let's just take it out. The mass of the proton is much larger than the mass of the electron. It's 1.67. 1.67 times 10 to minus 27. Okay? So the mass of the proton, those two numbers you don't have to know. But what you have to know is that the mass of the proton is approximately 2,000 times the mass of the electron. Okay? Can you remember that? 2,000 times? The charge is the same, but not the mass. The masses are completely different. That shows the distinction between one quantity and the other. Okay? That shows a very important distinction in between one quantity, the quantity of electric charge, and the quantity of the mass. The other quantity, that's the mass. That's what you have to remember. Here you go. I'm going to, now you know, compared to the mass of the proton, the mass of the electron is what? Identical, much greater, or much less, right? Just refer to that piece of information that we have in there. Okay? So when you remove electrons from a metal cup, what happens to the metal cup? happens to the final charge of the metal cup? You are subtracting negative charges of the metal cup. What happens? The metal cup becomes positively charged. Okay? The force that bonds atoms together, remember I told you, is the electric force. The electrical force rules supreme at the microscopic level. We didn't talk about nuclear force. There is a nuclear force, but we didn't talk about that. Okay? So you don't have to worry about that. Gravitational force is very small compared to the electrical force. So let's see. Here you go. What's the difference between gravitational and electric forces? Right? You know that the gravitational force is always attractive, right? But the electric force is what? It's both attractive and repulsive. They don't, they don't act at shorter distances, Electric forces act over shorter distance. No, they behave the same way as the gravitational force. Are weaker, you cannot say it's weaker. We can say it's weaker at the microscopic level, but when you have planet-sized objects, the gravitational force is going to be stronger. Okay, they both obey the inverse square law. Yes, so it's not that this is not a difference. Okay, so the main difference is that the electric forces both repel and attract objects. We're talking about, here you go, electric field lines about a point. Oh, here you go, electric field lines about a point charge. We did that, right? Extending what? In circles, outward when the charge is positive, outwards when the charge is negative. Let's go back to the drawing. Here you go. That's positive charge. That's the negative charge. Here's the inward, here's outward. So you should know what the answer is. 8:40. Any more questions? Okay. So
Yes, Professor.
Yeah, go ahead.
Oh, so I thought that there was only up to homework 8, but I saw that there was also a homework 9, but I did not see that in where the PDFs are.
Well, we do not know yet whether we're gonna have homework 9, so hang in there. Okay, I do not know if there will be time to cover magnetism, so hang in there. I didn't prepare homework 9 yet. Okay.
Oh, okay.
Let's see if you have time. I will upload in there. If I don't upload there, that's because you don't need to do it.
Oh, okay. And out of all of my homeworks, will by any chance my lowest score be dropped, or is it just for the exams?
Yeah, well, I will drop the lowest score of the homework as well. Yeah, I'll do that.
Oh, okay.
Well. Okay. I'll do that as well. The homework and the partial exam. I don't drop the final exam. Only the partial exam. Final exam.
So, okay, so out of the first 3, and then you drop 1. So you just drop 1 homework, right?
Yeah, just 1 homework. That's right.
Okay, got it.
Okay, 8:41, and so we have what? Let me give you a little map. What you're going to look. Okay, we have electric charges, electric force, electric polarization. What else are you going to see? Let me put it here for you. Electric potential. I'm not going to talk about electric potential yet. Okay, but I want you to know what's going to come. And then electric sources. For sources of electric potential. Here you go. A battery is a device that has electric energy there that you can use to power an electrical device. What else you have to know? I'm going to explain electric potential later on. It's a little bit difficult to understand, okay? But what is easier to understand is electric current. Electric current is rather easy to understand. Okay, electric current. Think about your electric charge right in here. I'm gonna copy that and paste. Okay, here you go. Okay, this electric charge can be made to move. If the velocity is zero, if the velocity of this charge is zero, you have no electric current. No electric current, okay? So electric current is related to the velocity of electric charge. If the electric charge is moving, here you go. If the electric charge has a speed, then you do have an electric current. It's just the same concept of water current. Water current is water in motion. Here you go. I'm gonna get it here. We put this electric charge to move, and we create what we call an electric current, V. Right here. You get the idea? That's a very simple concept to explain without going through much detail, okay? So we have 5 more minutes to go. I think we can stop here. I didn't want to waste this opportunity to tell you about electric current. And then next time we're going to cover the other concepts here, okay? So yeah, it looks like we are not going to have homework 9. We won't have time to do magnetism. So we're going to have only 8 homeworks, which I'm going to finish chapter 8 next time. Okay? And next, let's see. Wait a minute. Oh, wait a minute. No, it looks like we can cover homework. Yeah, it looks like we can. Yeah, we can cover magnetism next Tuesday. That's what you're going to do. Okay? Let's do like, I'll finish electricity next Thursday. We're going to have an exam. And then we do magnetism on Tuesday. I will prepare the homework for that. Watch for that. Okay? And then on Thursday, we do a review and the final exam. That's what's the plan for. That's the plan for next week. Okay, plan for the upcoming days. Okay, Thursday, finish electricity, chapter 8. Chapter 8, and what else? We're gonna do exam 3 from, let's say, 7:30 p.m. to 8:50 p.m. Tuesday next week, start magnetism, chapter 9. Try to finish it. I will prepare the homework 9. I'll post there. And Thursday next week, what we're going to do, review the material for the final. We're going to do let's do a 2-hour exam from 6:50. So let's see, from 5 p.m. to 6:50 p.m. Review the material for the final. From 6:50 p.m. to 8:50 because it's involved the whole, more material. Let's do this exam 2 hour long, final exam. Try to finish it. Okay, so that's what we have. Is 8:48 already.
Professor, how much questions will the exam have?
Let's see, we're having 20 to 30 questions for the partial exam, right? I still have to decide that. It certainly is going to be more than 30, okay? Maybe 35, 40, because we have more time to do the exam, 2 hours. Okay, I still have to decide. It's going to be more than 30, definitely, maybe 35 to 40. I still have to prepare that, haven't decided. So. But the final exam, you should expect, let's see, we covered chapter 1 and 2 in exam 1, covered chapter 3 in exam 2, right? We are going to cover chapters 4 and 5 in exam 3, okay? So we still have chapters 6, 7, 8, and 9 to be covered. So we're talking about 1, 2, 3, 4, 5. Yeah, you should expect, 50% of these chapters in the final exam, and 50%, 50-50, 50-50,
I also have a question, Professor.
Yeah.
So you said this Thursday before the exam, we're finishing up chapter 5. So we're covering chapter 6, 7, 8, 9 next week before the exam?
So let me see. What's your question again? I didn't understand.
Yeah, you just said that we're going to finish up chapter 5 before the exam 3 this Thursday.
Well,
And I was asking, is chapter 6, 7, and 8, 9 going to be covered next class before the final exam?
No, I said that chapters 4 and 5 is the material for exam 3. Okay, that's what I said. Here you go. Let me see here. Finish
Yes,
with
but
chapter
I was
8, right,
asking,
on Thursday. Chapter 9 on Tuesday next week, right? That's what I said, right? And then Thursday next week we're going to review all the material and the final exam. And then what I said exam 1, we covered chapter 1, right? We covered chapter 1. That was what I said here, 1 and 2. Exam 2 was just chapter 3, right? Just chapter 3. And exam 3 was chapter 4 and 5. Make sense? Does it clarify now? 4 and 5. That's what I said. And then we have homework that's due, right? We have homework that's due. Want me to cover that? Review that with you? Here you go. Homework for chapters 4, let's see. Homework 6 is due next time. Homework for chapters 4 and 5 is due today. Homework 6 is due on Thursday, this coming Thursday. Homework 7 next Tuesday, and homework 8 and 9 at the last day of class. Okay? Is that clear? Okay, so it's 8:52 already. We can stop now, and I see you the day after tomorrow.
Thank you, Professor.
Welcome.
Have a good night.
You too.